Now, we'll take up one more problem, the problem number 61. A steel tube of 50 mm OD and 10 mm thick is fitted into a copper tube of ID 50 mm and 10 mm thick. They are connected by using 20 mm diameter pins at its ends as shown in the figure. So this is here we have the steel tube of OD. So this is the outer one. From here to here it is 50 and 10 mm thick. So that means it should be inside this 10 mm thick. They are connected by using 20 mm diameter pins. So this is the diameter pin 20 mm at its ends as shown in this figure. So if the length of the compound bar is 600 mm, find the stresses produced in the tubes and pins when the temperature is raised by 25 degrees centigrade. Given alpha S is 12 into 10 to the power of minus 6 per degree centigrade, alpha C equals 17.5 into 10 to the power of minus 6 per degree centigrade. Young's modulus is 2 into 10 to the power of 5 Newton per mm square, and Young's modulus of copper EC will be equal to 1.2 into 10 to the power of 5 Newton per mm square. So copper tube ID, the copper tube, this is the ID of copper tube, which is 50 and again 10 mm thick. So you're going to get it as 70 mm. So how to solve this problem? So here first temperature is T will be equal to 25 degrees centigrade. Area of copper, which is AC, pi by 4 into 70 square minus 50 square. On simplification, you will going to get it as 1884.956 mm square. Area of steel, which is AS, is pi by 4 into 50 square minus 30 square. On simplification, you will going to get it as 1256.637 mm square. As the free expansion of copper is more than that of the free expansion of steel, so the compressive stress will going to be developed on copper, and whereas the steel will going to produce with the tensile stress to keep the same in the position. For equilibrium, what is PS will be equal to PC. So what is PS? PS is nothing but sigma S into ES will be equal to sigma C into EC. So what is that? Sigma S into area of steel is 1256.637. You substitute that value, equals sigma C into 1884.956. So on simplification, sigma S will be equal to 1.5 into sigma C. Also we know that what is that delta S plus delta C will be equal to alpha C into T into L, that is the free expansion of steel, coefficient of free expansion of copper, minus alpha S into T into L. So because one is the compressive stress will be induced in the copper, and tensile stress will be induced in the steel bar. So that is equal to, on simplification, as LS is equal to LC, which is equal to L, which is 600. So here PS into L by AS into ES plus PC into L by AC into EC will be equal to alpha C minus alpha S into T into L. So sigma S by ES plus sigma C by EC will be equal to alpha C minus alpha S into T, because L will be get cancelled. So we know what is sigma S, it is 1.5 times sigma C by ES, which is 2 into 10 to the power of 5, plus sigma C by 1.2 into 10 to the power of 5, which is equal to 17.5 into 10 to the power of minus 6 minus 12 into 10 to the power of minus 6 into 25. So here what happens? So you just take 1.5 into sigma C, which is 1.5 into 10 to the power of minus 5 into sigma C, plus sigma C into 2 into 10 to the power of 5, that divided by 2 into 10 to the power of 5 into 1.2 into 10 to the power of 5. So that will be equal to, simplification of this is 1.375 into 10 to the power of minus 4. So stress induced in the copper tube will be sigma C, which is equal to 8.684 Newton per mm square. So what we are doing here is basically taking the taking the LCM, that is 1.5 into sigma C into 1.5 into, it is 1.2 into 10 to the power of 5 here, and sigma C into 2 into 10 to the power of 5 divided by 2 into 10 to the power of 5 into 1.2 into 10 to the power of 5 will be equal to 1.375 into 10 to the power of minus 4 on simplification of this. So stress induced in the copper tube will be equal to sigma C. So when you cross multiply and divide, sigma C will be equal to 8.684 Newton per mm square, which is compressive in nature. Similarly, stress induced in the steel tube will be sigma S will be equal to, what is that sigma S? Sigma S is nothing but 1.5 into sigma C, which is here what we have substituted, 1.5 into sigma C. Your 1.5 into sigma C is 8.684. So again, which will be 13.026, which is Newton per mm square. Since the stress is the thermal expansion is more, so it will going to be in the tensile stress. Now similarly, stress induced in the pin tau P will be equal to P by 2 into AP, because we have two pins there. So sigma S into AS or sigma C into AC divided by 2 into AP. So you substitute the value of 13.026 into 1256.637 divided by 2 into what is area of the pin. Area of the pin is pi by 4 into 20 square. On simplification, you will going to get, which is equal to 26.052 Newton per mm square, which is shear stress. Because once it is expands here, it will be expands along the length of the surface. So naturally, it should be shear, so that it will going to break the pin into two parts. So this is all. We will be able to solve this problem. Now we're going to take up one more problem. A composite bar made of aluminium and steel is held between two supports, which is as shown in the figure. The bars are free at temperature of 42 degrees centigrade. What will be the stresses in the two bars when the temperature drops to 24 degrees centigrade? If A, supports are unyielding, and B, the supports come nearer to each other by 0.1. The cross-sectional area of steel bar is 160 mm square and that of the aluminium bar is 240 mm square. So Young's modulus of aluminium equals 0.7 into 10 to the power of 5 Newton per mm square. Young's modulus of steel is 2 into 10 to the power of 5 Newton per mm square. Coefficient of thermal expansion of aluminium is 24 into 10 to the power of minus 6 per degree centigrade. And coefficient of steel, thermal expansion of steel equals 12 into 10 to the power of minus 6. So to solve this problem, so here the bar which is shown in the figure having the steel bar having 500 mm length and the aluminium bar having 250 mm length. So here when the temperature drops to 25 degrees, so that means 24 degrees, so the T will be equal to temperature drop 42 minus 24 will be equal to 18 degree centigrade. Therefore, the free contraction is alpha S into T into LA or alpha S into T into LS plus alpha C into T into alpha A into T into LA will be equal to, take out T as the common factor, which will be T into alpha S into LS plus alpha A into LA. So substitute the values, that is T is 18, that is the temperature drop is 18 degrees centigrade because 42 to 24, into substitute the values of alpha S into LS plus alpha A into LA, which is 12 into 10 to the power of minus 6 into length of steel bar is 500 plus 24 into 10 to the power of minus 6 into 250. So on simplification, the free contraction is 0.216 mm. As the free contraction is restricted by the supports, tensile stress will be set up in the steel bar as that of the aluminium bar. However, the force in the aluminium bar is equal to the force in the steel bar because it is PS will be equal to PA because both the ends are fixed. So that is sigma S into AS will be equal to sigma A into AA. Sigma S into 160 will be equal to sigma A into 240. So sigma S will be equal to 1.5 times sigma A. Elongation of the steel bar due to temperature stress delta S is PS into LS by AS into ES will be equal to, you know that PS by AS is sigma S into LS by ES. So we know sigma S is nothing but 1.5. So you first sigma S into length of steel bar is 500 divided by 2 into 10 to the power of 5. That will be equal to 2.5 into 10 to the power of minus 3 into sigma S Therefore, elongation of aluminum bar due to temperature stress delta A will be PA into LA by AA into EA, which is sigma A into LA by EA. So sigma A into LA is 250 by 0.7 into 10 to the power of minus 10 to the power of 5, which will be 3.57 into 10 to the power of minus 3 into sigma A. So also a supports are unyielding, that is delta S plus delta A is equal to 0.216. That is already we obtained from here, which is the free contraction. So 0.2196, 0.2196. So what is delta A? Delta S is nothing but here 2.5 into 10 to the power of minus 3 into sigma S plus 3.57 into 10 to the power of minus 3 into sigma A. So that is what we are expanding here. But that is equal to 0.216. So we want the sigma S to be substituted. 2.5 into 10 to the power of minus 3 into sigma S is nothing but 1.5 into sigma A. Substitute the value of that, that is into 1.5 into sigma A plus 3.57 into 10 to the power of minus 3 into sigma A will be equal to 0.216. Therefore, the stress induced in the aluminum bar is sigma A, which is equal to, on simplification, you will go and get it as 29.5 Newton per mm square, which is of tensile. Similarly, what happens? Stress induced in the steel bar, which is sigma S, will be equal to 1.5 times sigma A, that is 1.5 into 29.5, which will be equal to 44.25 Newton per mm square, which is again is of tensile. When the supports comes closer by 0.1, so what is that? Delta S plus delta A will be equal to 0.216 minus 0.1, so that will be equal to 0.116. So again you substitute these values, that is 2.5 into 10 to the power of minus 3 into sigma S here, which is 1.5 times sigma A, that will be plus 3.57 into 10 to the power of minus 3 into sigma A will be equal to 0.116. So substitute these values. So you're going to get it as, on simplification, stress induced in the aluminum bar is sigma A, which is equal to 15.846 Newton per mm square. Again, it is tensile. And when stress induced in the steel bar, which is sigma S, will be equal to 1.5 times sigma A. 1.5 into 15.846 will be equal to 23.77 Newton per mm square, which is again of tensile. So this is how you will be able to solve these problems. If you find these problems are useful, please subscribe to my channel. Thank you.